Good morning and welcome to the second episode of the Energy Insight webinar series. My name is Przemysław Kaliński and I work as a product category manager at IMI Hydronic Engineering, taking care of thermostatic controls family. Today, we will focus on energy savings in household radiator heating systems. You will see a very interesting example of how AFC, automatic flow control technology, can secure hydronic balancing and optimize heating systems. I'm sure you are all aware of the current situation. Inflation and the energy prices have sparked a cost of living crisis across Europe. Governments are stepping to reduce the pressure on businesses and household owners by introducing new legislation and subsidies. IMI Hydronic AFC technology supports these efforts and reduces energy consumption. Potential gains can be really significant, and as thanks to the heating system optimization, we can save up to 30% or sometimes even more. I'm pleased to kick off this webinar and give a voice to Robert Green, our Hydronic College expert who will present AFC control in detail and share guidelines on how to optimize your system. If you have any questions, please post them in the chat, as there will be a Q&A session at the end of this webinar. Robert, the stage is yours.
Thank you, Przemek, and good morning and good afternoon to everybody that's tuned in this afternoon or this morning. Hopefully today we're going to give you a really nice introduction to the energy saving possibilities within radiant heating systems. So what we've got is we've got a bit of an example of actually a real home that was lightly renovated in Austria, and we're going to look at some of the potential savings and actually a little bit quickly run through a process of how we might get there. So without further ado, let's go through the presentation. And as I said, today we will be talking about the energy savings in radiant heating systems. A bit of a quick agenda. We're going to start with an introduction to these potential energy savings. We're then going to go covering a little quickly new systems versus renovation of old systems. And we're actually going to concentrate on the renovation of an existing system in a building. And we're going to go through the steps, including the calculations required, an energy comparison, calculated energy comparison for the upgrades and changes, and also at the end, some final practical steps. And then we will have a conclusion, put it all together, give us an overview of what we're looking at in terms of savings and how we get there. And at the end, we're going to have a little bit of a question and answer session. So as Przemek alluded to, if you do have any questions at all during the presentation, please plop them in the chat and we will do our best to answer them at the end of this session. So we're going to start by talking about energy savings by optimizing the hydronic system. And by the hydronic system, we mean the waterborne network that is carrying heat throughout your building. And actually, optimizing the heating system can generate savings of around 30% or sometimes even more. And it can do this by avoiding the efficiency reduction in condensation boilers, because condensating boilers, when we take a modern boiler and we've got told it's got an efficiency of say 90% efficient, which means that 90% of the gas used is converted into heat that is directly heating the water to heat your home, that is only going to be under a strict set of conditions. And actually, in quite a lot of systems, those conditions aren't actually met. And by optimizing the hydronic system, we're able to look at optimizing this. And we can also reduce the required heating demand to make sure we're comfortable. And on the side of that, we can also optimize the energy efficiency of the distribution system. So by that, I'm talking about reducing the consumption of the pump on the system. So it's other savings we can get there also. And Also by guaranteeing a stable and accurate room temperature. So we can never forget the reason we have a heating system in a home is to give an accurate, stable room temperature so we get indoor comfort. And actually, if we look at that 30% in terms of pounds and pence, if we take the estimated average yearly gas cost for a typical UK home is around about £1,200 per year. So you could be into talking of savings of up to sort of £300, £350 per year if we're going on a particularly inefficient system and optimizing it completely. And as I say, this optimization, the savings are actually coming from other devices. Our device itself is not saving energy, but it is setting your system so you can enable your boilers and your pumps to run as efficiently as possible. And how are we going to do that? We need to have a plan on how to do that. And if we look at improving the efficiency of production units, so with production units, I'm talking about boilers, chillers, heat exchangers, heat pumps, and some of the factors reducing them. One of the most common factors is actually a reduction in differential temperature or an increase in return temperature coming back to that boiler. So in condensing boilers, in order for my boiler to condense, in order to use that additional heat exchange of the exhaust gases, my water must come back at below around 63 degrees, something like that. It needs to be below that figure. And if it sits above there, we don't condense. We lose that efficiency of the heat exchange on the exhaust gases. And how do we do that? We look at that by providing variable flow instead of constant flow. Because in order to compensate for load in systems, we must vary the flow through that system. And if we then look at the distribution side of things, we're looking at factors which are reducing the energy costs of the pumps. So reducing how much electrical energy my pump is using to move that water throughout the system. And that then is going to provide my optimum benefit for variable speed pumping. And finally, we want to look at the energy savings potential by accurate room temperature control. And that is going to mean the issue of oversizing. So generally, a lot of systems are going to be oversized. The heat losses for the system may not have been calculated very accurately, if at all. A radiator was put in that is the width of the window, and it's going to be oversized. You're going to be overheating rooms. And if we're overheating rooms, we're wasting energy purely by overheating that room. If I'm comfortable at 20 degrees and I overheat to 22 degrees, I need to use more heat energy to get my room up to 22 degrees. So therefore, I'm wasting energy to get there. And we can look at this, and how we're going to look at it is actually by hydraulic balancing. So a very quick overview on hydraulic balancing in two-pipe radiator systems. In order to balance, normally we have to calculate that piping network because we need to know what the pressure losses are throughout all of the pipes in my network. So we can get real presettings for our radiator valves to overcome those differences in piping network pressure losses. In new systems, this is principally possible, but it takes a long time, which is why it's not often done in practice. In a new system, I have all of the pipework layouts. I know how long the pipe is. I know from this radiator, there's 10 meters of pipe. From this one, there's 25 meters of pipe, so on and so forth. I can calculate what my pressure losses in all my pipe segments are. But like I said, can take a long time, so it's not often done in practice. In renovating systems, you have to know that there's even more additional obstacles. We have no plan of the plant. The system, I don't know really exactly where my pipework runs. Unknown ways with the pipes. Again, where do these pipes run? Are my radiators all piped in parallel? Are they running off separate branches? All of this sort of stuff. And eventually, we can't measure the pipe length. If I can't measure the pipe length, I do not know what the hydraulic resistance is through that pipe network. So I can't calculate how much additional differential pressure I need to take from each of my TRVs, my radiator valves. And Again, an existing system is not going to be fully clean. We're going to have an unknown pipe friction factor. My pipes may be slightly degraded, they may be slightly blocked, which means we're going to have more resistance, and we don't know that from a calculation point of view. So in conclusion, we can practically say seeing a correct pressure loss calculation in an existing system is practically impossible. So it's almost impossible to calculate pressure losses. And we're going to talk about in the coming slides actually how our automatic flow control technology can overcome for not having these pressure losses calculated. So we're going to talk about how to generate savings in a two-pipe radiator systems in an easy way. So if we look at a new system versus a renovation, we can actually say that balancing of the system is essential in new installs as well as in the renovation process. Now, today we are actually going to concentrate on this renovation process itself. And the only correctly dimensioned and adjusted systems are guaranteeing an energy efficient operation. You could buy the very best pump, the very best boiler, the very best TRVs, the very best radiators. If you're not setting up that system correctly, you're not guaranteeing an energy efficient operation. A boiler running at 94% efficiency only runs at that under a set of conditions. If your system means you are not allowed to get those conditions, you will not get that efficiency. You will be using more gas in your system to provide the same level of heat, and you could even be overheating your system, which means you're using even more energy to get there. In new installs, there's the advantage of having a good calculation basis. Therefore, with the right settings for an energy efficient operation can be found quite easily in a new install. In a renovation, as we saw previously, this is a lot harder to come by. But actually, using our automatic flow technology helps enormously in both cases, because what this is going to do, this is going to compensate automatically for my differences in pressure. So I'm going to get the exact amount of flow volume I need through every radiator, regardless of the pressure losses leading up to that radiator, as long as I install and set these valves correctly. So as I said, we're going to talk about renovation of an existing plant. And we're going to talk about a system where the old heating system's kept and is going to be recalculated. And how we're going to do that, we need to have a plan of how to do this. So what we're going to start with is diagnosing the correct heat demand of the rooms. How much heating do I need in each room of my household? We are then going to recalculate our radiator sizes. So by recalculating our radiator sizes, we are going to ensure the radiators are going to emit the required heat to get my rooms to the right temperature. And we're going to do that by getting the right supply and return temperature and the correct flow rate through our radiator. And with our AFC technology, we are able to get this correct flow accurately, as long as we've calculated it. And that's what we're looking at today, is this calculation. We're then going to look at the mounting and presetting of the new valves. And we're going to look at the possibility of lowering the supply and return temperatures to increase the efficiency of a condensing boiler. So we're going to now look at reducing the heat output of a system. So direct savings on a reduction of how much heating, how much load you need. And actually, we're also going to look at improving the efficiency of that boiler. So we're going to burn less gas for a given amount of output. And looking at increased comfort and lowering the costs of heating. So we're going to be comfortable and we're going to be less spending less money, saving more energy. So let's actually have a look at that and how we're going to do it. And we're going to optimize an existing system. We're now going to look at a house in Austria that we've previously run some calculations on, and actually we've actually put an install in there. And it was one of my colleagues' son's home where we did this renovation process. Actually, In the end, we did a full renovation and they put underfloor heating in, but we can still look at this process to see what we've done to calculate some potential savings if we weren't doing this full renovation style of things. So we want to optimize my existing radiator system. So the first thing we need to do is, like I said, collect data and calculate the heat demand. We then want to check the radiator power, and we're going to do this with an adopted supply temperature. We need to choose a design supply temperature in order to calculate how much heat my radiators are producing, so we can then look at adjusting these temperatures to get how the heat correction required. From there, we can calculate the flow of each radiator. Once I calculate the flow, I can calculate the set point very easily of my AFC eclipse valves. We can then determine the power consumption of the pump and look at the total potential of energy savings by this light renovation, just changing the TRVs on my system. So if we look at the first process, how do we get the heat demand without the correct calculation? Now, there is lots of heat demand calculations available throughout Europe, throughout the world, lots of different ways of doing it. Today, we're going to look at a very simple process where we have a ground view of the house, a knowledge on how old the building is and what condition it is in, where the house is placed, and knowledge about the local heat demand calculations. Now, that in every locality, you should have some form of local heat demand calculation per year of property. So like we said, we're looking at the ground view of our model house. And this is a one-family house situated somewhere in Austria. And we can see in total, we have 8 separate rooms downstairs. And if we look at the living space, is just under 110 meters squared. It was constructed in 1982 in good condition. So we need to know, how big is the specific heat demand? What is the heat demand per room? And what is the total heat demand? Once we know this specific heat demand figure, it's relatively easy for me to calculate my heat demand per room and my total heat demand of my building. And we've got some charts we can do to look at this. So here's a chart based on the standard DIN EN 15378. And this shows me area related heat demand depending on different construction years for properties in Austria. I must state this is for properties in Austria. Other areas are going to have different specific heat demand types. And if we take a look at our building, we said it was 1982. So you can see we're going to choose this lower blue line here. And if we look at the the sleeping room, we have a room area of 14.4 meters squared. So if we take 14.4 meters squared, that's going to give me a heat demand for my room of around 1400 watts. So we know in my sleeping room, I require 1400 watts to keep my room at a comfortable temperature at maximum load. So only when it is, say, -4 degrees outside is when I need this 1400 watts. Obviously, that load's going to reduce in warmer temperatures, but when we are maximum load, we need 1400 watts to heat that room. So what we can then do is we can record the area of each room and the required room temperature. This is very important as well, the required room temperature. We can then, from the charts we saw previously, determine the heat demand per room. And you can see here, this is the heat demand calculated for every room with a total requirement of just under 10 kilowatts, 9,800 watts. And what we're going to say is rooms with 2 equal radiators are set for 50% each. So if you look, the dining room radiator has got 2 radiators. So what we've done, total requirement is 1300 watts, and we've provided 50% of the heating demand in each of those radiators. Also, for the corridor, because there is no outer wall, only an entrance door, we're going to lose less heat from there. So we've actually halved the heat requirement in the corridor area, because otherwise we'd be overheating that corridor. And you can see we've also recorded all of the required room temperatures. So you can see 21 degrees in most of the rooms, 24 degrees in the bathroom, and 22 degrees in the living room. And we'll come on to that shortly as to why that's so important to check. We now, after we've done that, we want to record the sizes and types of all the radiators in my system. So you can see in here, we've recorded what the type of radiator is, how high it is, and how long it is. Because if we want to calculate how much heat that radiator can possibly emit, we need to know something about its construction. And we can then look at how to estimate the heat demand on my radiators. So with my radiator data, I can go through a manual process by help of the manufacturer's tables to recalculate radiators. It's quite a long-winded process, so I'm not going to go into any more detail, but a more convenient solution is to actually use our application, which is called HyTools, and we can get very good results for all of the different radiators with a deviation of less than about 10% on there, if we use this example. So if we take the example of HyTools, and we then calculate the radiator power and flow coming from, we would use a virtual supply and return temperature. So if we look at this here, if we take our system, and I will show you now how we can do this. Hopefully this is going to allow me to broadcast my screen. No. Let's try again. Okay, come on. Let's try again. Unfortunately, a bit of technology problems, but bear with me a second, we'll get there. No, sorry. Unfortunately, I was hoping we could show you a live view of the application, but my screen share isn't working this afternoon. But anyway, in order to calculate the radiator power, what we need to do within our application is set a supply temperature, a return temperature, and a required room temperature for a given size of radiator. So in this case, you can see we're looking at the sleeping room. And we've told it's a type 21 radiator with a height of 600 millimeters and a length of 1,120 millimeters or 1.12 meters. And you can see we're going to choose a virtual supply and return temperature to get an idea of how much power we get in this radiator. And if I choose a supply temperature of 65, a return temperature of 60, so I can then ensure my boiler is condensing, and my required room temperature is 21 degrees C, you can see my radiator power is 1.43 kilowatts, which we can then look at, so 1.4 or 1,425 watts. So if we look at that in a bit of detail, what I can then do is calculate an over-dimensioning factor. So we can see we've calculated a flow rate of 82 litres an hour, and that is going to give me on this radiator, when it's producing 1,425 watts, 75-degree flow, 60-degree return, and 21 degrees room temperature. And we can see in the case, our over-dimensioning factor is 1.02, or as an example, the radiator in the sleeping room is the perfect size at those temperatures. And we can see we've got our calculated flow to get those temperatures. But what you can also see is actually this over-dimensioning factor varies per room. So pretty much all of the radiators, with the exception of the kids' room, are over-dimensioned. So you can see they're at 1.65. Some of them in particular are 1.96, i.e. nearly twice the amount of heat we're outputting. Now, we were saying we wanted to do a light renovation. We didn't want to be changing pipework, removing radiators, all of this sort of stuff. We just wanted to do a light renovation by changing these TRVs. What we can then do, it's varying between the different rooms because of this uncalculated radiators. So what I can do is to correct the values with high oversizing factors, I have to be recalculated by changing the return temperature until the oversizing factor is approximately 1. So if, for example, we take the dining room where the over dimensioning is 1.96, we needed 650 watts. The radiator was delivering nearly 1300 watts. They were nearly twice the size they needed to be. If we go back into our High Tools application, and now we look at it, and what we want to do is, this is the example here. We had a Type 21 radiator that was 1 meter long and 0.6 meters tall. We started with 75, 60, 21 temperatures, and we got an output of 1.272 kilowatts, 1,272 watts, which was twice what we needed. I can go into my temperatures and adjust my temperature. If I reduce that return temperature, I'm going to reduce the amount of power that radiator is going to emit. And actually, if I reduce my required return temperature down to 35 degrees, you'll see my power calculated is now 650 watts, 653 watts, pretty much exactly what I needed. And you'll also see we've recalculated the flow at 14 litres per hour. So if we were to set both of these radiators for a flow of 14 litres per hour, we can enable my system to run efficiently and heat that dining room to the required temperatures. Unfortunately, I couldn't show you live on there because my screen share wasn't working, but get in contact with your local area representative. I'm sure they'll be able to give you a demonstration on this application. So some example calculations we actually made some example calculations. We wanted to go through, we've got a simulation software called HECOS where we can simulate full load conditions of a system, because we wanted to look at the potential energy savings we got. So we designed this system on our software and made some calculations. First, we calculated with the old standard radiator valves, including pipes, mixing valve, boiler, so on and so forth, with an 80-degree supply temperature, i.e. design supply temperature for this system. In reality, the system would be unbalanced. So we took this example with an unbalanced system, and the existing pump would have to be set to maximum speed because to get my living room supplied with the right temperature. In an unbalanced system, certain areas are going to be unfavored, and we're going to need to push up the mass flow rate through the system in order to obtain the correct heat in my unfavored areas, which means we're going to be outputting more heat, we're going to be pushing more flow through the system, and we're going to be having issues about my return temperature. So if we look at this plant, the theoretical values we've calculated to get a warm living room with an unbalanced plant is we need a real output of 12 kilowatts, a necessary flow of 1,184 kilograms an hour. That required a pumping head of 20 kilopascals and real operating temperatures, a supply temperature of 80 degrees and a return temperature of 71 degrees, i.e. if I'm returning at 71 degrees C, my boiler is not condensing. I am not using the efficiency that my boiler has been designed for. So that is looking at the system side of things, the boiler, the heat production unit. We can also look at, we said about savings within the system, and that's going to be the power consumption of the pump. So if we look at the different working points of a standard pump, these are some pump charts of a Velo pump. And if we look at our design conditions, where we were running 20 kilopascals and 1.2 meters cubed per hour, theoretical consumption to get the living room warm is 47 watts. In reality, what happens is at practical operation, everything's put at full power, because if your room is not satisfied, everything gets pushed to full power. You push the pump right up, we produce more flow and more differential pressure, which means my pump is using even more energy. So it's using 62 watts. Versus if we look at the optimized system, where we've calculated and optimized it with our Eclipse valves, we need slightly more differential pressure on my pump than we did at design, but we needed a lower flow rate. So you can see on there that we're only using now around 35 watts of pumping energy. So if we take a comparison of all of my energy savings on the systems, if we compare the old unbalanced system with the recalculated system using the Eclipse, we can get a perfect compensation for the oversizing factors with really good energy savings. We're actually saving twice on the heating system, because if we look at the heating, if we look at our old unbalanced system, we are emitting over 12 kilowatts of heating power. We need a flow rate of 1,650 litres and a supply temperature of 80 degrees, which means I'm returning back to my boiler above 71 degrees. So first saving, actually when we recalculate it, we take 20% off my load. So I'm producing 20% less heat, but still keeping my building comfortable. I've dramatically reduced my flow rate. I've slightly reduced my supply temperature, but most importantly, I've dramatically reduced my return temperature here. So my boiler now can condense. I am running my boiler as efficiently as it possibly can be. Also on this, we're saving energy on the pumps, as we saw on the previous slide. So you can see we're also running roughly 50% less energy into the pump, or half. The pumping power is roughly a little bit more than half, but you can see also worth mentioning on the pump, reducing both the pump head and the flow is going to result in a longer working lifetime of that pump. The pump isn't working as hard, therefore it's going to last you longer. So that is our comparison for savings, and you can see hopefully where they all come from nicely. Let's have a quick look at the practical steps. So what do we need to do practically in order to set this system? It's actually very simple. We've already run all of our calculations. We know all of our set points. All we do, we need to drain the system and then exchange the valves. That's valves now exchange. We've replaced the old TRVs with the AFC Eclipse TRV, ensuring that they are installed with the correct flow direction. And finally, we look at the presetting, and the presetting is really, really easy. Actually, we have a number between 1 and 15 on our presetting. Each of these numbers is the flow in litres per hour divided by 10. So if we wanted a flow of 50 litres per hour, we only need to simply set that valve to position 5, and then that's going to set the flow rate into my system, which means my system is then going to be set and operating as efficiently as it can be. So in conclusion, with little work, we can create a high rate of success. The AFC technique is an essential and helpful function to get a high efficiency rate. If the system is only partly renovated with new eclipse valves, the comfort will be increased and the energy consumption is reduced by up to 30%. Potentially a £300 per year saving you could be looking at here. And if you do so in systems with condensing boilers, the return temperature can be guaranteed and the boiler starts condensing, so we get an increased efficiency rate. This last point here is the most important point when we're looking at this. Ensuring that our boilers are condensing, we are running our boilers in the most efficient way possible. So that's the end of my presentation for this morning. Hope you've all enjoyed it, and we will now open the floor for any questions.
Rob, many thanks for this great presentation. Let's move to the Q&A session. It seems you were crystal clear as we got only a few questions, so let's proceed with them right now. Maybe we can start with a question from Henrik. He is asking if we have similar heat demand diagrams for other countries, or at least where we can find them.
We personally don't, but they should be available through. I'd recommend contacting your local building services engineers conglomerate. So, like in for example, we've got the Chartered Institute of Building Services Engineers in the UK, who would have access to all of this data. But there should be standards for all of your countries.
Good. Maybe we can take the next question. Yeah, Amalie, and that is a very good question. She wants to know if this renovation help public buildings to meet the 19 degrees temperature restrictions.
Yes. In particular, very important with these 19-degree restrictions. So if we talk about comfort in buildings, humans are generally comfortable to plus or minus half a degree. So 19 degrees is sitting on the limit of where you're too cold in a building. You're not too cold, but you drop a little bit below that and you're too cold. By renovating and ensuring you have the right load, the right flow in all of your radiators in a building, and you've recalculated those radiators to achieve that temperature, the building should be uniformly comfortable. You should uniformly have the right temperature. So therefore, you're going to have less changes of temperature. So there's a much lower likelihood that your temperature in your building is going to drop below that 19 degrees in certain areas. Because human nature is, if I'm cold, I don't go to, well, I do because I'm a nerd, but human nature generally, if you're too cold in your building, you don't look at the stat and go, oh, I've set it to 19 degrees. Let's try 19.5. Human nature is, it's cold, let's put it up to 24. You put it up to 24, you use more energy, you overheat the building, either get complaints from, if you can't adjust it, you get complaints you're cold. If you can adjust it, you use too much energy and overheat your building. So actually, really important with this sort of reduced temperature restrictions in public buildings.
And if I could just only add on top of it, we have two very good products which comply with this 19 degrees regulation. First of all, you can use one of the K heads. We have a product with the setting range from 6 up to 19 degrees of centigrade. So that means that you cannot exceed 19 degrees of centigrade, even though you set up the maximum value on the thermostatic head. That is the one solution. The next solution is the Halo B. Halo B is a great product dedicated to public buildings. And what is quite unique about this product, it is having the tamper-proof design. It means that if you want to change the setting of the temperature, you have to remove you have to remove the plug from the front of the thermostatic head. Then using a special key, you make a setting and put the plug again. And that means that even you will rotate the head constantly, the temperature will not change and it will be kept at 19 degrees of centigrade. So just to summarize, we have two products which are just perfect solution for this. One of the K heads, you will find the code number in the datasheet. It is a product with setting range up to 19 degrees of centigrade. And finally, the Halo B. That are our two solutions. Good. And we have one more question from Maxim about the role of the AFC technology in energy reduction. So, Rob, if you could summarize very shortly.
Yeah, sure. So the role of AFC technology is there to ensure a accurate balance with minimal work in your system, which is going to mean that your boilers and your pumps are going to be running as efficiently as possible.
Yeah, that is a long one from Bartosz, which just arrived. Is the app dedicated to plumber installer? Okay, so it is all about having a tool which can support the plumber and installer in making the proper hydronic balancing.
Yeah, so well, we've got our High Tools app, which allows you to calculate radiator sizes fairly accurately, and gets you able to set systems. If you're looking for something that's actually going to give you install this, it gives you this energy saving, we haven't got that. It would be, as I say, it's down to the proper balancing. If I'm honest, when I talk about proper balancing with end user customers, it's obviously going to change in the last 12 months because the landscape's changed massively. 12 months ago, when you talked about balancing with customers, end users, it's all about indoor comfort. The key is indoor comfort because they were worried about having the rooms at the right temperatures. And that's what balancing gives you, is it ensures you have all of your rooms, your house comes up to the right temperature in order. We don't have, for example, I'm not great. My heating system hasn't been balanced. I haven't got round to it. I should have done. I've been here 5 years now. I'll hold my hands up and say I should have done it. But like some of my areas get warm. So for example, I've got my thermostat in my hallway, and there's quite often my hallway will get hot, turn the thermostat off, but there'll be certain areas like my living room might still be a bit cold. So you can still get it's that indoor comfort, but an actual application. It's not. We do the app for doing calculations, but as a sort of simplification for end users, we don't. We've got guides. We have guides available. There is an online guide for radiant heating systems and potential energy savings there.
Okay, thanks, Rob. The next one.
Yes, very easy. If you've got existing IMI TRVs, we even sell a tool so you can completely change the insert without even draining the system. So really easy to change them. We sell a tool that's literally, it's a case of you bolt the tool onto the TRV, you extract the old insert, drain a very small amount of water, change the insert over in the tool, put the new one back in, and it's changed, and then you can go and set it all up, as long as you're using existing IMI TRVs, obviously.
I think that we can still have the one more question. Andre is asking about the eSafe system. So basically everything which you described, which can happen automatically. Rob, are you aware of the eSafe system? Frankly speaking,
Not something I've come across, no.
Yeah, frankly speaking, it's the very first time I hear about it. Andre, if you could just send some more details, it would be great. We have a next question which just arrived from Ricard.
On that one, Richard, I would 100% recommend getting in contact with your local, I'm not sure where you're based, but if you get in contact with your local sales engineer, they'll be able to advise you. We actually have a full engineering center that can do complete drawings and things to optimize, to set, and what would we recommend on your system and how would we recommend to set it up. We've got a lot of guides online, sort of technical brochures, but in the first instance, I would 100% recommend getting in contact with your local representative.
Good. Let's give a second for the last minute questions to arrive, because we have replied for all the questions. Okay, seems nothing more is coming in. So before we close this webinar, I would like to encourage you to contact your local IMI representative in case you have any further questions related to the AFC technology. And please keep in mind that IMI have many solutions that support heating system optimization and to reduce energy consumption. So do not hesitate. IMI experts are here to support you. Good. Thanks a lot for today, and I wish you a great day.
Yeah, thanks for tuning in, everybody, and have a great day.
Yeah, thanks a lot. Bye.